Now, to review what we talked about with the math and kind of really explain the concepts that come from the math, is that if you have a long wheelbase and four wheels with the same coefficient of friction, if this length L is really big, since L is equal to D1 and plus D2, either D1 or D2 are going to be big, or both of them are going to be big. And the effect will be that either torque 1 or torque 2 will be big as well. Now, the reason that is not good is because if torque 1 or torque 2 are big, your motors are going to come closer to stalling. You do not want either of these two numbers to, well, definitely you don't want them even close to stall torque. You don't want them to be over stall torque, or you're not going to be able to turn. Ideally, you want them to be around half of stall torque, so we can operate at max power the way we've discussed for other mechanisms. Or even less, you're not going to turn slower as a result. So you don't want these numbers to get very big. So here's a couple of ways, like I mentioned earlier, to avoid this. Torque 1, or torque in general, is going to be equal to our frictional force times our distance. So if it's torque 1, it'll be frictional force 1 and distance 1. If distance 1 is really great and you can't do anything about it, well, then the other option is to decrease frictional force. The way we decrease frictional force is we decrease one of the components of it. So you can either decrease normal force by making the weight less on one of the sides or on the entire robot, or you can decrease the coefficient of friction. Now, you can't just, like say, okay, I want this coefficient of friction to be small. You actually have to change something physical about it, right? So our treaded wheels have more of a higher coefficient of friction than our omni wheels. So something you can do is you can change one set or both sets to omni wheels. And you generally want to do that if you're going to change one set to omni wheels. You want to do that for the distant side, which has a greater distance here, because it's going to have a greater impact on our torque. Because if our distance is greater, well, decreasing our frictional force is going to have a greater effect because they're being multiplied. So one thing you can do is you can change one set of wheels to omni wheels, or you can change all of them to omni wheels. If that doesn't work for you, other options are change your L. Now, let's say you need to have wheels on the outside because you don't want your robot to tip over. There's two ways that you can change your L without getting rid of the outer wheels. Option number one, as we mentioned before, is changing to an 8-wheel drive, where you keep your outer wheels, but you have another set of wheels that just sits a little bit lower. So this will be your L. Now let's say you have these in such a way that you rock back and forth, which will often happen with this kind of setup. You want to make this distance really minimal so that you don't rock too much. But let's say you do rock, you do want to actually gear these outer wheels so that they're moving with these inner wheels, so that if you are on one side or the other, well, your L will just become this distance or this distance. And no matter what orientation you fall into, your motors can still handle turning on that end. Now, the other option you have to shorten your L is to go with a 6-wheel drive with a center drop. So if we have a 6-wheel drive with a center drop, I drew this a little bit wrong. Let me redraw that. If you have a 6 wheel with a center drop, you might be saying, okay, there are 3 wheels here, but there are 3 on each side. If you have a 6 wheel with a center drop, your L will be either here or here, depending on which side you're tipping onto as you drive around. You got to be careful with this because you don't want to make this distance too big or you will tip over as you drive. But this will work as well. Okay. Now that we've dealt with turning and how to improve it and what causes robots not to be able to turn, let's talk about tipping. So over here I have a free body diagram of your clawbots with a chassis and wheels, a tower, a rotating arm, an arm, a claw, and a ball that it's holding. Now, I'm not going to ask you to do any math with this because we got the center of gravity calculations down, and I really just wanted you to be able to conceptually understand, look at a free body diagram and figure out about where the center of gravity would be. So over here, there's a lot of weight up top. There's 3 pounds up here, 2 pounds up here, 2 pounds up here, a pound up here. Your center of gravity is probably going to be somewhere here, somewhere in this range. It's like a hot zone for your center of gravity, somewhere in there. And you can go ahead and you can do the calculations on it and figure out where it is. But it's going to be somewhere around here. Now, as you drove around your robots, especially when you picked up those balls, you probably noticed that the robot was tipping over a lot. And the reason for this was you had a very high center of gravity. As you're driving around, your drive base acts as a lever that can swing this way. You can almost treat this wheel as a fulcrum. Not almost. You can treat this wheel as a fulcrum. So as you drive around, and this top part of your robot wants to go this way, this acts as a fulcrum and wants to pop a wheelie and go over. Now the rule of thumb is, if you have a robot and you just look at it as 3 points, let's say you have one wheel, so this is one outer wheel, this is another outer wheel, and this is your center of gravity. If this center of gravity ever reaches the point where horizontally it's gone past your fulcrum, you're going to tip over. So let's say you pop a wheelie. So you pop a wheelie, so I'm going to draw this again, but now we've popped a wheelie, so we're like this. If this is your center of gravity and these are your wheels, as soon as you cross this point here, your robot is tipping over. Now you might be able to catch it suddenly by driving this wheel this way and fixing it. But, in general, that's the rule. If this point crosses this line, you're tipping over. So the question is, okay, what do we do as designers of robots to deal with this? Well, what you do is you try to get this center of gravity to be, first of all, as low as possible, because that will create stability and stop you from popping up and down as you drive around. And you want to get it as close to the center as possible. If your center of gravity is over here, it's going to be extremely difficult for you to tip over. Extremely difficult. But if it's up here, it's going to be very easy. So when you had your clawbots, your center of gravity was really high, especially when you picked up that ball. So when you were driving around, it was really easy to tip over. Now what can you do? Let's use the clawbot as an example to lower your center of gravity. I want you to think about that for homework, and that's what I want you to answer. Okay? I'll see you guys next time.